Hey y'all, today we're going to be looking at how to compare solubilities between two or more different compounds. In order to do this, what we're going to start with is looking at how we determine molar solubility, and then once we have molar solubility, how we can use it to compare relative solubilities. We're also going to look at a quick shortcut to how we can compare solubilities in certain circumstances without even having to solve for that molar solubility. So let's get started. Molar solubility is how many moles of any substance will dissolve into a solution until it's saturated. When we look at the solubility, though, we don't always look at it as molar solubility. In some cases, it might be gram solubility, where it's grams per liter, or even a type of gram solubility where it's grams per 100 milliliters. So relative solubilities can be compared as long as we're looking at the same unit, whether it's molar solubility or gram solubility. We need to make sure we're comparing apples to apples. Also, in the case of any solubility comparison, we need to make sure we're comparing any solubilities at the same temperature, and in the case of gases, at the same atmospheric pressure. Reason for this is because those play a large role in relative solubilities, and we're going to talk about those a little bit later. So you're aware there are a number of factors that can impact solubility. The most commonly changed factor that we're going to look at is temperature. However, there are other things that will impact it as well. For molecular substances, for example, the relative polarity and size of molecules will impact its solubility. For gases, the atmospheric pressure will impact its solubility. In ionic compounds, things that impact Coulomb's law, such as ion charge and size, will impact solubility. One other thing to be aware of is that there are things that impact the rates at which things do dissolve, but don't change the molar solubilities. For instance, stirring a solution will help to speed up the dissolving process. However, it will not change the solubility of the substance that's dissolving. The solution will reach the same exact saturation point. It'll just do it faster. As I said earlier, temperature is really the biggest player for us in this course when it comes to determining the different solubilities of any one substance. Normally, when we're looking at dissolving processes, we're comparing them at the same temperature. But what if we start changing the temperature? In this situation, we have to think back to thermochemistry and how thermochemistry impacts equilibrium. Remember that in a delta H, which is positive, an increase in temperature will favor the endothermic direction, which is the forward direction. If the delta H of the forward direction is negative, then a decrease in temperature will favor the forward direction. So if we think about dissolving as always a forward direction, the process of dissolving that is endothermic would be favored with an increase in temperature, and any dissolving process that's exothermic would be favored with a decrease in temperature. The most important skill you're going to learn in this video is how to compare the solubilities of two different compounds. So assuming the compounds are being dissolved at the same temperature, one of the easiest ways to do this is simply by looking at their KSPs, but with the caveat, you can only do this if they have the same number of ions. For example, you can compare two compounds that have two ions, one cation and one anion. At the same time, you can compare two compounds that have three ions. So maybe one has two cations and one anion. The other has one cation and two anions. You could compare those as well. And the reason we can compare those directly is because if you remember back to our equilibrium expressions, our KSPs, any two compounds with the same number of ions would have the same value of S in terms of whether it's S squared for any compound with two ions or 4S cubed for any compound with three ions. And remember, it doesn't matter if those ions are the anion or the cation, because in the end, the value of S is going to be multiplied in the same way and then squared in the same way. So again, we can compare KSPs only if we're in a situation where we're comparing compounds with the same number of ions. In that situation, where we do have the same number of ions in two different compounds, the compound that has the greater KSP value will be more soluble. it'll have the greater molar solubility. So when we look at the KSPs, remember, the larger the KSP, the further the reaction is favoring the forward direction. The forward direction of solubility is the dissolving process. So the larger the KSP, the greater the solubility. But remember, we can only compare compounds with the same number of ions when we are doing this. So let's just do an example. These two compounds, lead 2 sulfate and magnesium carbonate, both have 2 ions. They have 1 cation and 1 anion. Now, when we're comparing these two, we're going to have given the KSPs. So the KSP of the lead 2 sulfate is 6.3 times 10 to the negative 7th, and the KSP for the magnesium carbonate is 3.5 times 10 to the negative 8th. Now, because they have the same number of ions, I can compare directly using the KSP expression, but only because they have the same number of ions. For example, in this case, I know that the lead 2 sulfate has a greater KSP than the magnesium carbonate. Therefore, it is more soluble. But let's prove it anyways. We're going to solve for the molar solubilities of each of these. Now, the nice thing is, both of them would have an equilibrium expression equal to S squared. KSP equals S squared. So for the lead 2 sulfate, it would be KSP equals the concentration of Pb2 plus times the concentration of SO42 minus. Both of those, if we did a Rice table, would end up with S, and therefore KSP equals S squared. When we solve for S, the S value, the molar solubility of lead 2 sulfate is 7.9 times 10 to the negative 4th. Now we compare that to the magnesium carbonate, where when we solve for S, the value of S is 1.8 times 10 to the negative 4th. And you can see that the molar solubility of the lead 2 sulfate is greater than the molar solubility of the magnesium carbonate. Again, we could use the KSP only because it had the same number of ions. Comparing the solubilities of two different compounds that have different numbers of ions is not all that tricky. The key here is we just have to solve for the value of S in each one. So if they have 2 ions in one and 3 ions in the other, then in the one we're going to solve using the KSP equals S squared, and in the other we'll solve using the KSP equals 4S cubed. When we do this, though, we're solving for 2 different S values, and once we do solve for the S values, the larger the S value, the more soluble that compound is. Now be aware, when they have 2 different numbers of ions, the KSP might actually be smaller in the more soluble compound, and the KSP might be larger in the less soluble compound. And it's because when we're solving for that S value, we're using a different equation to go from KSP to S. Let's do a practice problem where we look at 2 compounds that have different numbers of ions. In this situation, we're going to compare magnesium carbonate, which has a KSP of 3.5 times 10 to the negative 8th, and calcium fluoride, which has a KSP of 3.9 times 10 to the negative 11th. Now, when we compare these two, we can't use their KSP values because they have different numbers of ions. The magnesium carbonate has 2, 1 cation, 1 anion. Meanwhile, the calcium fluoride has 3, 1 cation and 2 anions, the 2 fluoride ions. That means we have to solve for our S values in each situation. To solve for the S value of my magnesium carbonate, I'm going to take the square root of the KSP, because KSP is equal to S squared. So therefore, the square root of my KSP in this case is going to equal 1.8 times 10 to the negative 4th. For the calcium fluoride, the KSP is equal to 4S cubed. So what I need to do is I need to take my KSP, divide it by 4, and then take the cubed root, or raise it to the 1/3 power. When I do that, the S value that I get is 2.1 times 10 to the negative 4th, which is actually greater than the solubility of my magnesium carbonate. 2.1 times 10 to the negative 4th is greater than 1.8 times 10 to the negative 4th. That means that the calcium fluoride, even though it has a smaller KSP, has a greater molar solubility. This is, again, why we cannot use KSP to determine relative solubilities if the 2 compounds have different numbers of ions. You have to solve for S. So that wraps up today's video. Today, we determined how we can compare relative solubilities of different substances. Remember, if we're in a situation where the two different compounds have the same number of ions, we can use their KSPs directly. However, if the two compounds have different numbers of ions, we have to solve for the molar solubility. Once we do that, the one with the greater molar solubility will be the one with the greater solubility. This video was written, directed, and produced by Bryn Garrity. Thank you all for watching it. I hope you enjoyed it, and I'll see you in the next one.